Welcome to video number 2 for section 14.2, where we will be taking a look at some examples for two new chi-square tests, the test for homogeneity and the test for independence. So let's remind ourselves exactly what those tests are again. We talked about them in video number 1. Goodness of fit, of course, was section 14.1, where we're comparing the distributions for categorical variables about a single population. Tests for homogeneity and tests for association, let's remember that homogeneity involves two or more populations, and we'll be comparing one categorical variable. In tests for association or independence, we will be looking at two categorical variables, and that will involve looking at a single population. With our two new chi-square tests, we will be working with two-way tables, so it's important that you understand what two-way tables are all about. You were introduced to these in Chapter 4 when we were dealing with marginal probabilities and conditional probabilities. And I'll show you a slide example here real soon about a two-way table. And these tables are made up of a certain number of rows and a certain number of columns, and we'll use this notation right here to represent these two-way tables. The chi-square test will involve us putting all of our observed counts into the two-way table, and then we're going to have to calculate the expected counts for each one of those observed values. And in order to do that, we're going to have to use this formula right down here. And I will be demonstrating how we use that in a moment. First, let's take a look at a two-way table on our next slide. Here we have a two-way table that is full of data involving the party affiliation for males and females. And you can see that we took a random sample from each population, so we ended up with a total of 36. We had 20 males and 16 females, and we asked each one of these populations what their party affiliation was, and you can see here that we had 11 males say they were Democrats, 7 said they were Republicans, and 2 said they were independent. And then we also see the responses for the females as well. And in this test for homogeneity, we want to know, does the distribution of proportions for females and males end up being the same for their party affiliation? So before we figure out what all the expected values should be for these cells, we're going to take a look at the first step in the inference procedure for this test, and that would involve, of course, the hypothesis, null and alternative. So when you state the hypothesis for the test for homogeneity, the very generic version here is shown right here. We are trying to test to see if the proportions are different between the two populations. So we're going to make the assumption or the claim that all of the proportions for these categories are the same, and then we are going to test to see if we have any evidence that some of these proportions are not the same between the populations. So in our example with the males and the females and the party affiliation, we are going to say in our null the proportion of Democrats, Republicans, and independents are the same within the populations of males and females. And then the alternative would be to say that not all the proportions in the null are equal. Okay, let's move on to step number 2, where we're going to state the test. We're going to take a look at the conditions. We will be calculating our expected values, and then we'll be ready to actually carry out the test and figure out our test statistic, the chi-square number. The conditions for the chi-square test of homogeneity of populations is these two right here. And we want to make sure that the two populations of interest are independent, so we're taking an SRS from each population. And again, we want to make sure all of the expected cell counts are greater than 1 and no more than 20% or less than 5. That's the same as the goodness of fit test condition as well. The condition for expected counts, all being greater than 1 and no more than 20% being less than 5, that's right here. We make use of this formula that we have. I showed this to you in an earlier slide. So for each cell that we have in our original two-way table for the observed counts, we are going to take the row times the column divided by the sample size to get these expected counts, so we can prove that most of them are greater than 1 and most are greater than 5. So if I want to know what would I expect for male Democrats, right here, I would take the row total times the column total divided by the total sample size, and that would be 10. And I can do this for each cell and figure out all the expected counts. Now in class we'll show you how to put this into your matrix in your calculator, and we'll be able to run the chi-square test on our calculator quite easily as long as we get these numbers into a matrix. When you run the test, all the expected counts will be put into a matrix, and you can just pull them off your calculator and write those down to prove that your condition has been met. Next is actually computing the chi-square number from your observed and expected counts. So we go back to that formula right here. Oops. This one right here. So if you go to your two-way tables and take each cell and the corresponding observed and expected accounts and subtract those and divide it by the expected, you'll get all your chi-square numbers. You'll have to list those, add them up, and that will be your test statistic. When you're doing the p-value, you can use that chi-square CDF in your calculator. You just have to make sure you get your degrees of freedom right. This time the degrees of freedom will be the number of rows minus 1 times the number of columns minus 1. So in our example with the party affiliation between males and females, we had 2 rows, so that'll be 1. And we had 3 columns, so that'd be 2. Our degree of freedom would be 2. So as we go to chi-square CDF, we would put in our chi-square number here first, its right tail, and then we'd put 2 right there. Now the chi-square number for our example here with party affiliation between males and females is 0.855. And if you put that into chi-square CDF, you end up with a p-value of 0.652137. So that's a fairly high p-value, which means we would fail to reject, and we'd go to step number 4 and state a conclusion in the context of the problem, which means we would say we have very weak evidence to suggest that the proportions can't spell today, proportions, move up here, of Democrats, Republicans, and Independents for males and females is different. We are going to assume that the distribution of those proportions for both males and females are the same. And that is our first example involving the test for homogeneity. In our next video, we'll take a look at the test for independence.